Okay, so in the flipped class video, we considered we wanted to find dy dx for the curve given by x cubed plus y cubed equals 6xy. And the way we did this in that video is we set f of xy to be x cubed plus y cubed minus 6xy. And then our curve here is given by f of xy equals 0. And now the way we found the dy dx was we used chain rule and we said f is a function of x and a function of y, and y is still a function of x. So this can be somewhat confusing though, because we specifically said we can't represent the curve as y is equal to f of x. So how does this part here make sense then? So what we're doing is we're using that we can locally represent the function or the curve as a function. So we can break our curve up. So maybe let's first recall what our curve looked like. So it looks something like this. It came down, touched around, went around like this, then off like this. So this was our curve where f of xy was equal to 0. So now we can break this up into a bunch of pieces, or 3 pieces in this case, and each of those will be a function. So we can start by just looking at just this part here, and notice that part is basically from here up, following it around till we get up to here. And so this is a function. And then we can consider the other pieces that are still left over. And so I have the part that finishes this part of the loop, and then the part that goes off like this. And we can see each of the orange pieces here is a function, and all together they give us the whole curve. So even though we can't write the entire curve as y is equal to a function of x, at each point we can view y as a function of x. So when we look up here at this chain rule, that's what we're doing. This part here is just breaking into the orange pieces. So that's what we're really doing. One thing to note is this doesn't work if we're at a spot where the tangent line would be vertical, which makes sense because we said that our method didn't work if f sub y was 0 at a particular point. So maybe let's recall back what we were doing then. So how we found that derivative was we said since we had f of xy is equal to 0, if we use chain rule, we take the derivative of each side. Well, the derivative of 0 is 0, and then I have f sub x times dx, which is just 1, plus f sub y dy dx. And so this is just f sub x plus f sub y dy dx. And then we just solve this for dy dx, and we get negative f sub x over f sub y. And that's how we found our dy dx. So let's go ahead and work a simple example of this before we get on to some applications. So let's find the equation of the tangent line of sine of x plus y equals 2x minus 2y, and we want this at the point pi. And so we can check. If we plug pi in for x and pi in for y, we get 0 on each side, so it satisfies this equation. Okay, so our first step is we're going to set f of xy to be sine of x plus y minus 2x plus 2y. And then we can find our partial derivatives. So f sub x, take the derivative with respect to x, I'm going to get a cosine of x plus y, and then the derivative of inside is just the derivative of x, which is just 1, and then I'm going to get a minus 2. F sub y is going to be cosine of x plus y, and then again the derivative of y is 1, and I'm going to get a plus 2. Now I want to evaluate these at the point pi pi, so this is cosine of 2 pi minus 2, so this is 1 minus 2, which is minus 1, and f sub y at pi pi is cosine of 2 pi plus 2, which is 3. So that means my dy dx at pi pi, remember this is negative f sub x at pi pi over f sub y at pi pi. So this is negative 1 over 3. So the slope here of the tangent line is 1/3. And so our tangent line is y minus pi is equal to 1/3 x minus pi. So one thing I want to point out here is in Calculus 1, it is usually taught a different way to do this where there's no motivation given, you're just told how to do this. So what we would do in this situation, just to kind of make sure we see both methods, in case you happen to have seen the other one before, is we differentiate this just like we would normally, and we treat y as if it's an x, but then we put a y prime next to it each time. So if I differentiate this, I get a cosine of x plus y, and then I want the derivative of what's inside, which is 1 plus, and then treat the y like a 1, or like an x, we get 1, but then we have to put a y prime with it. And then we do 2 minus 2, but then I need a y prime, so I differentiated a y. And then we want to solve for the y prime, so I'd have cosine of x plus y plus cosine of x plus y prime equals 2 minus 2y prime. Get all the y primes together, so cosine of x plus y plus 2 times y prime is equal to 2 minus cosine of x plus y. And now what we should notice here is that this happens to be, if you look back above, this is exactly our partial derivative, or this is the negative of the partial derivative for our f, and this is our partial derivative for y. So when we solve this for y prime, which is of course dy dx, I do get the negative fx xy over fy xy. So it's the exact same process. It just really doesn't have any motivation because you're just told just put a y prime whenever you differentiate the y. Whereas when we do the chain rule, we see that there's a reason why we do this. But that's how that method works, and that's the one that's normally encountered in a first class in calculus. But for this, I think it's better to actually understand what's actually going on. Okay, so now let's move towards some examples. These are called related rates examples. So we're going to do some typical ones. Okay, so we have a ladder leaning against the side of a building. The ladder begins to slide down the wall, with the bottom of the ladder moving away from the wall at 2 meters per second. Okay, so once the bottom of the ladder is 6 meters away from the wall, how fast is the top of the ladder moving down the wall? So when we're doing problems like this, the best thing to start with is we're going to start with a picture of what's going on, so we can put some labels on things. So let's say we have our ladder leaning like this. We know the length of the ladder is 10. And now let's call the base here x and the height here y. And notice that x and y are both changing with respect to time. So we can make a list of what we know and what we want. That kind of helps us guide ourselves through the problem. So we know we're told dx dt is 2 meters per second. That's how fast the base is moving away. And we can also use Pythagorean theorem to say x squared plus y squared is equal to 10 squared. And what do we want to know? We want to know dy dt when x is equal to 6. So to set this up, let's write f of xy to be x squared plus y squared minus 100. So we just took this and turned it into an equation. And so we want when f of xy is equal to 0, that gives us our curve. And now our chain rule here says we have f, which is a function of x, and a function of y, and then we know each of the two variables, x and y, is changing with respect to t, where t is our time variable here. So if we take this equation and we apply chain rule to it, I'm going to get 0 for the derivative of 0, and I get f sub x dx dt, following this side down, plus f sub y dy dt. And now we do our calculations. Notice our f up here, we take the derivative of that. So f sub x is just 2x. F sub y is 2y. And then we knew dx dt is 2 meters per second. So we have 0 is equal to 2x. Then I have a 2 plus 2y dy dt. I can certainly cancel this 2 and then solve for dy dt. So this is negative 2x over y. And now we're given, remember we want when x is equal to 6, and so we can use the equation, the Pythagorean theorem, to find what y is then. So when x is equal to 6, I know y squared is 100 minus 6 squared. So y squared is equal to 64. So y is equal to 8. So then that allows me to plug into my equation. So dy dt is equal to minus 2 times 6 over 8. So this is minus 3 halves, and then the units are meters per second. And then just to be super careful, if we look back at the phrasing of the problem, it says how fast is the top moving down the wall. So this is saying what the change in y is. So the top is moving down the wall at 3 halves meters per second. So we do have to be a little careful with the negative signs and how things are worded. Okay, let's look at another example. Try different type of problem, but we'll try to apply the same process. Okay, so our setup here, we have a spotlight on the ground and it's shining against a wall 12 meters away. A 2-meter tall person is walking away from the spotlight towards the wall at 1.6 meters per second. And what we want to know is how fast is the length of their shadow on the wall changing when they're 4 meters from the wall. So just like last problem, let's go ahead and try to start this with a picture. So start with my wall, and then put my spotlight over here, and the spotlight is shining on the wall, towards the wall, and let's say our person here is standing here. So we can call this height here y. We know this whole distance here is 12. I know the height of the person is 2. And then I know the person's moving in this direction. So let's call this variable x, because x is what, they're both sides are what's changing, but x is what we're going to know. They're going 2 meters or 1.6 meters per second towards the wall. And so that means this distance here has to be 12 minus x. So what we know from this, we know dx dt is 1.6 is negative 1.6 meters per second. And where does that negative sign come from? Well, when we're thinking of the sign of the derivative, we know positive means increasing and negative means decreasing. And if we look at x, as the person walks towards the wall, that's a negative. That's getting smaller, so we're going to put that at negative. And what do we want? We want dy dt when x is equal to 4. Now it's perfectly fine. You could have, where we labeled 12 minus x, you could have called that x, and then the other part would have been 12 minus x. Either way would work. They're both going to come out the same in the end, so whichever you're more comfortable with. Now, how are we going to work this problem? Well, what we can see is we have similar triangles here. So I can say that y over 12, which is the big triangle, the height versus the base of the big triangle. Then we can look at the smaller triangle here. So we have this triangle, and then we have the big full triangle. So that smaller triangle has a height of 2 with a base of 12 minus x. So if I solve this for y, so when we solve this for y, we get y is equal to 24 over 12 minus x. And now we'll go ahead and do the same thing. We'll set up our equation. And we want to consider when f of xy is equal to 0. And just like before, we have f as a function of x and y, which are both functions of t. So we differentiate this equation over here and get 0 is f sub x dx dt plus f sub y dy dt. And now we need to do these calculations. So f sub y is the easiest because the y only appears there is just y, so that's just going to be 1. F sub x, on the other hand, we have the minus 24, and then when I differentiate 12 minus x to the minus first power, I get 12 minus x squared, but then I have another negative, so that makes it positive, and then the derivative of 12 minus x is minus 1. So this is minus 24 over 12 minus x squared. So now I have most of everything I need. So we want x to be equal to 4. So if we plug that into our equation up here, if x is 4, that means y is 24 over 12 minus 4, which is 24 over 8. So this is at a height, this is at 3. We aren't actually even going to need that. There aren't any y's left in the problem. So if I solve dy dt, I get negative f sub x dx dt over f sub y. But f sub y was equal to 1, so this is negative 24 over 12 minus x squared. And I've got minus 1.6 for that, and then the f sub y was equal to 1. So dy dt when x is equal to 4 is 24 over 12 minus 4 squared times negative 1.6. And so this comes out to be negative 0.6 meters per second. Okay, so we can see when the x is as they're walking towards the wall, the shadow is going to be getting smaller, which is what we would expect from since we get a negative sign here. Okay, let's look at another example. Okay, so we have two ships. At noon, they're basically one's just directly west of the other by 100 kilometers. But ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. And we want to know how fast is the distance between the ships changing at 4 p.m. So as always, let's start with a picture. So this is what it would look like at noon. They'd be 100 kilometers directly across from each other. But now the ship B is going to move up here, and in the future be some distance up here, and it's still moving in this direction. So let's call this distance y. And ship A will have moved down some distance here. Let's call this x, and it's going in that direction. And what we're asking ourselves is how fast is the distance between them changing? So this is that distance. Let's call that length there L, for length between the ships. And so what we want here is I want to know what dl dt is. And since I want this at 4 p.m., the t will be equal to 4 because everything is measured in hours here. And what do we know? Well, we know a few things. We know dx dt, so the distance x here is increasing at 35 kilometers per hour. dy dt is increasing 25 kilometers per hour. And then we're also going to have an equation here for L. So it's easiest if we redraw this a bit. So if I have L here, I know the distance between the lines there is 100. And then this distance here, think of taking this triangle and flipping it over. So take this triangle and flip it over. So it's going the full distance there. This would be x plus y. Right, so think of taking this and flipping it over. So you get the whole thing there. This is our big triangle. It looks like this, and then we have y there and 100 there. So that means we know L squared is 100 squared plus x plus y squared. So those are the things we know. So we're going to do the same process we've been doing. We're going to take this equation and we're going to make it into an f. So f, now it's going to depend on x, y, and L. This is going to be L squared minus 100 squared minus x plus y squared. And we want when that's equal to 0. So as usual, we take the derivative. So I'm going to get f sub x times dx dt plus f sub y dy dt plus f sub l dl dt. And notice right here, this is what we want. And now we're just going to go ahead and fill these things in. So f sub x, if I take the derivative of this equation here with respect to x, I'm going to get a negative 2x plus y. If I take with respect to y, I'm going to get a negative 2x plus y. And if I take it with respect to L, I get 2L. And now we can fill a lot of this stuff in already. So I have the f sub x is minus 2x plus y. We said the dx dt was 35, so let's fill that in. F sub y is negative 2x plus y. And then we said this was 25. And then f sub l is 2l, and of course dl dt is what we're looking for. So in order to finish this problem, we need to know what x, y, and l are. And we want this, remember, when t is equal to 4. Well, after 4 hours, x is going to be 35 times 4, which is 140. Y is going to be 25 times 4, which is 100. And L, we use this equation up here, this one right here. So L is going to be square root of 100 squared plus 140 plus 100 squared. And if we work this out, this comes out to be 260. So plugging everything in, here now I have 0. I can cancel a 2 off from all of these. And so I have negative, I have 240 times 35 minus 240 times 25 plus 260 dl dt. So solving for dl dt, this is equal to 240 times 35 plus 240 times 25 all over 260, which is 14,160 over 260, which is about 54.46 kilometers per hour. Okay, let's try one more example. Okay, so we have an inverted conical tank, basically an upside down cone. Water's leaking out at 10,000 centimeters cubed per minute, and at the same time water's being pumped into the tank at a constant rate. Okay, so the tank has a height of 600 centimeters, and the diameter at the top of the tank is 400 centimeters. Okay, so if the water level is rising at 20 centimeters per minute, when the height of the water in the tank is 200 centimeters, find the rate the water is flowing into the tank. So we'll start this like we've started all of them so far, and we're going to draw a picture. So here's a picture of our tank. We know that the diameter of the top is 400, so that means the radius is 200. And we know the height of the entire thing is 600. Now we have water in the tank. We'll say, obviously this is changing as the water goes up or down. So this is a radius of r and a height of h. Now how do we phrase this into and out of the tank in terms of something we can work with? Well, let's think about it with the amount of water in the tank. If that's given by V, say, so V is the volume of water in the tank, then dV dt, this is the change of the volume of water in the tank. Well, how do we measure that? Well, that would be the amount flowing in. This would be the rate it's coming in minus the rate it's going out. And the rate it's coming in, we don't know. Let's just call that A. And we know the rate going out is 10,000. We're trying to find the rate it's going in, so we solve for that. And we see that's dV dt plus 10,000. So what we want is we want to figure out now what dV dt is. And we want that when the height is 200. And now if we think about what we know that the height is changing at 20 centimeters per minute. So dH dt is 20. And we also know a formula for the volume, or at least you'd be given a formula for the volume. It's pi over 3 r squared h. Okay, so now note we have v as a function of h and a function of r, both of which are functions of t. So that means I have dV dt is v sub h dh dt plus v sub r dr dt. Now we want to fill these things in. So v sub h is just pi over 3 r squared. V sub r is 2 pi over 3 rh. And then we know that dh dt is 20. So far I have dv dt is equal to pi over 3 r squared times 20 plus 2 pi over 3 rh dr dt. So we have several things we don't know so far. We do know, I guess, we wanted our h to be 200, so we're eventually going to put in 200 for h. We need to figure out r and dr dt. So if we look at our cone again and we just look at it from the side, we can use similar triangles again. So remember, this would be r, this would be h, and then this is 200, and this full thing was 600. So our similar triangle says 200 over 600 should be r over h, or r is equal to 1/3 h. So now if I want when h is equal to 200, that would mean r should be 200 over 3. And then we can also take the derivative of this to say when dr dt is 1/3 dh dt. So this means this should be 20/3. And now we have everything we need to fill this in up here. So we see dv dt here. This is pi over 3. And then my r is 200 over 3 squared. And then we want that times 20. Plus, I have 2 pi over 3. R, which is 200 over 3. Times h, which is 200. And then that's dr dt. So that's times 20 over 3. And so now if we work this whole thing out and plug this into a calculator, we get this is about 1954768.76 centimeters cubed per minute. So that means A then, remember, is this thing plus 10,000. So this is 1964768.76 centimeters cubed per minute, or these are approximates. Or if we want to put this so it doesn't look so gigantic, we can change it into meters. So we see for these related rates problems, each one is kind of its own unique type of problem, but the strategy is the same for all of them. We're almost always going to draw a picture. We're going to label our picture. We're going to write down what do we know, what do we want to know, and then we work from there with our equations.